All right, we're taking a look at uniform circular motion. Today was horizontal circles, so all of these circles will be based on horizontal circles and not needing to do anything with gravity, because gravity is perpendicular to the forces causing those horizontal circles. A child on a merry-go-round is moving with a velocity of 1.35. Let's go ahead and fill that in our given velocity is 1.35. 1.2 meters is our radius, and they're looking for acceleration. So v squared over r, 1.35 squared divided by 1.2. We calculate that. We get the answer of, in a calculator, 1.519 meters per second square. All right, that's number one. Let's go to number two. Number two, the moon's nearly circular orbit around the Earth has a radius of 384,000 kilometers in a period of 27.3 days. What's the velocity of the moon? What's the centripetal acceleration of the moon? So two questions there. We can't let them go. Kilometers is not meters. Let's get it in meters. Multiply by 1,000. 384 million meters is the radius. 27.3 days is not seconds, but 27.3 days, if we multiply it by 24 hours in a day, 3,600 seconds in an hour. Multiply the tops, divide the bottoms. All the bottoms are 1, so nothing to worry about there. Canceling out units leaves us just with seconds. 27.3 times 24 times 3,600. Our period is in seconds. That capital T is period. It's the time in order to go through one cycle. 2,358,720 seconds. They're asking for the velocity and the acceleration. Velocity being 2 pi r over t. Well, we know what 2 is. We've got a button for pi on our calculator. They gave us the radius. We converted it to meters, and they gave us the period. We converted it to seconds. So 2 pi times 384 million divided by 2,358,720. I'm using the pi button on my calculator. If you prefer 3.14, function is what's important. Our answers will be close. The answer I got was 1,022.909 meters per second. Maybe that's 904. I think it's 904. So 1,022.904 meters per second. I know acceleration is v squared over r. So I'm going to take my velocity, I'm going to square it and divide by the radius. One zero two two point nine oh four squared divided by 384 million. 0.00272 meters per second square. A ball at the end of a string is 0.6 meters long, so radius is 0.6 meters. Ball makes 2 revolutions in 1 second. 2 revolutions in a second. So how long does it take to do 1 revolution? I can do 2 in a second. So in half a second, I can do 1. What is the velocity of the ball? What is the acceleration of the ball? How much tension in the string if it's connected to mass is 0.15 kilograms? We've already put down on our paper, but we know that the centripetal force is the tension. So when it asks for tension, it's asking for centripetal force. Tension in this case is the reason the ball goes in the circle. So we can set those equal to each other. We can calculate it either way. Velocity is 2 pi r over t. We have an r, we have a t, so we're just going to take 2 times pi times 0.6, and we're going to divide that by 0.5. That gets us our velocity. 7.54 meters per second. Next, it's asking for acceleration. And acceleration we know is v squared over r. It seems like it's just leading us through the problem. It had us solve our velocity first. Now that we have velocity, we can square it and divide by the radius. We can also set it up as 4 pi squared r over t squared. If we don't want to trust our previous solution, it's fine. Works either way. Once we put it in the calculator, we're getting 4 times pi squared times r times the radius divided by t squared. I'm getting 94.748 meters per second square. Finally, it asks us for tension. Tension is the centripetal force for this object, and centripetal force is calculated as mass times centripetal acceleration. The mass is 0.15. The acceleration is 94.748. I'm getting 14.212 newtons for my force. Number 4, a jet plane traveling at 500 meters per second, so my velocity is 500 meters per second, does a loop with a radius of 6,000 meters. So radius is 6,000 meters. What is the acceleration of the plane? We know acceleration is v squared over r, so we can just take our 500, square it, divide it by 6,000. That will get us the acceleration. It also asks us for how many g's. It says g is 10 meters per second, so if we just divide by 10, we'll know how many 10s there are or how many g's there are. Let's start with the acceleration, 500 squared divided by 6,000. Acceleration should be something close to 41.67 meters per second squared. 41.667 to be more precise, meters per second squared. It wants to know how many g's. Since g is a 10, it's how many 10s are there. So we're going to take our 41.667 and divide by 10. And we get 4.167 g's. What is the centripetal acceleration of the Earth? They gave us the mass of the Earth in its orbit around the sun. They give us the mass of the sun. Assume the Earth orbits in a circle with a radius of, so they give us the radius. They give us the mass of the Earth, the mass of the sun, the radius of that circular motion, and they want the acceleration. So in this problem, I want to approach it a little bit differently. I'm feeling like you could work it a number of different ways, and I feel like this might just be a little bit more direct. What is the centripetal force here? Isn't the centripetal force the force of gravity? Well, how do we calculate gravity? Force of gravity, it's gm1 times m2. Here, g times the mass of the sun times the mass of the Earth divided by radius squared. How do we calculate centripetal force? Well, it's the Earth that is going in the circular motion, so it would be mass of the Earth times the acceleration. Well, don't we have it simplified to calculate the acceleration now? It's set up to calculate for centripetal acceleration the constant g, 6.67 times 10 to the minus 11, times the mass of the sun, 1.99 times 10 to the 30, divided by the radius squared. They gave us the radius at 1.5 times 10 to the 11th power. Now, could we have calculated the velocity and then from the velocity calculated the acceleration? Where you could do 2 pi r over t. You know t is 1 year. Figure out how many seconds are in a year. Absolutely you could. This is just a little bit easier with no dimensional analysis, and we got 0.0059 meters per second square. There's more than one way to do it. Let's find the easiest. If a CD spins at 500 revolutions per minute, well, that's frequency. That's how many times you can do it in a set amount of time. We want to know how long does it take to do it once. So let's put our 500 revolutions over 1 minute and say 1 minute is 60 seconds. That tells us how many revolutions per second, because if we want seconds per revolution, we're looking for the inverse of that frequency. Period and frequency are inverses, but we want it in seconds so that it's in the units that we want. 8.333 revolutions per second. Since we want seconds per revolution, we're basically inverting the units, so we're going to invert the number. 8.33 to the -1 seconds per revolution. And we just put it in our calculator. There is a x to the -1 key. It's right above or right below. See, it's right above the x square key. And when we do that, we find out it's 0.12 seconds per revolution. So our capital T, our period, is 0.12 seconds. Did all that work just for one variable, but it's an important variable. We've got T is equal to 0.12. It says the diameter is 12 centimeters, so the radius would be 6 centimeters. But we don't do centimeters. 6 centimeters is 0.06 meters. What is the centripetal acceleration on the very edge of the CD? It's asking for AC. On the very edge of the CD is using the full radius. Let's go ahead and calculate that. Based on that information, the second half of the question says, what radius would you have the acceleration equal to the 35 meters per second square? We'll do that second, one problem at a time. If we're looking for AC and we know T and R, we're going to use the 4 pi square R over T square. It has the variable set up for what we need. So 4 times pi square times 0.06 divided by 0.12 squared. And don't forget the 0.12 is squared. Put that in our calculator. We'll get something around 164-ish. Should be 164.33, something like that. Oh, that's close. 164.493 meters per second square. Now, in the second half of this question, as you change positions on the CD, your period doesn't change. As a compact disc spins, no matter where you are on that CD, close to the center with a small radius or all the way at the outside edge with a larger radius, the time it takes to complete the circle is the same because the CD is intact. It's all connected. It finishes one lap at the same amount of time. So our period hasn't changed. It's still 0.12. But if you have a different radius, you'll have a different velocity. If you have a different radius, you have a different acceleration. So we're going to set this equal to 35 is equal to 4 pi square r over 0.12 squared. I'm multiplying the 0.12 squared to the other side. I'm going to divide by 4 and then divide by pi square. So many times people will divide by 4 pi square without the parentheses. The calculator thinks it's divide by 4 and then multiply by pi square. So do it one step at a time. The answer for your radius was 0.0128. Number 7, you've got a mass of 1,000 kilograms. You've got a radius of 50 meters. Coefficient of friction at 0.3. How fast? It's looking for velocity. Here, I'm really tempted to set up the force of friction is equal to the centripetal force. Force of friction is coefficient times force normal. But for a car, can't we see that force normal is balanced with force of gravity? The vertical forces are balanced. And if the force of gravity is calculated as mg, can't we say that force normal is equal to mg at this point? Well, if the force of friction is coefficient times force normal, couldn't we say that force of friction is coefficient times mg? Because force normal is equal to mg. So we're going to start with force of friction is equal to the centripetal force. Force of friction can be calculated as coefficient times force normal, and centripetal force can be calculated as mass times centripetal acceleration. We're going to change force normal to mg, and we're going to change acceleration to v squared over r. The m's cancel. We know g is 10, Little g is always 10 on Earth. Multiply the radius to the other side, and that sets it equal to v squared. The coefficient of friction is 0.3, g is 10, r is 50. So if we multiply that out, we get 150 is equal to v squared. So we just need the square root of 150, right? 0.3 times 10 times 50 is 150 is equal to v squared. So let's find out the square root of 150 in our calculators. I got 12.247 meters per second is my velocity. This is the kind of problem we need to be used to. Setting the type of force that is our centripetal force for horizontal circles, set them equal to each other, and just start breaking them down on how you calculate them until you get the variables you need or the variables you're looking for. Our centripetal force to spin this discus, think of a frisbee, is 280 newtons. Mass is 2 kilograms. Radius is 1 meter. What's the acceleration? What is the velocity? Well, acceleration does show up as Fc is equal to mac. Remember that equation? We have Fc, we have m, so AC should be 140 meters per second squared. Don't always lock yourself into calculating AC as v squared over r and then 4 pi square r over t squared. Next, we're looking for velocity. Well, AC is v squared over r. AC we said is 140. So that's v squared over r. R is 1. Let's just turn that into a 1 real quick. So then v squared is equal to 140. So what's the square root of 140? 11.832 meters per second is that velocity. And we only have a couple more to go. We'll be done in the next 5 minutes or so, maybe 6 minutes. A cord holding a 0.4 kilogram ball, so our force of tension is our centripetal force. The mass is 0.4 kilograms. If the tension exceeds 60, it's going to break, so we're going to use maximum tension and make it 60 newtons. How fast? We're looking for velocity. If the radius is 1.3 meters. Looks like, looking at this, I want to use Fc is equal to mac and then change the AC to v squared over r. It would give us everything we're looking for and contain everything that we have. So Fc is equal to m times v squared over r. We know that 60 is equal to 0.4 times v squared over 1.3. So take your 60, divide both sides by 0.4. That'll move the 0.4 to the left. So 60 divided by 0.4. And then multiply both sides by the 1.3. And then you'll have a number that's equal to v squared. So 195 is v squared. So what is the square root of 195? .964 meters per second is our velocity. 2 more questions, 4 more minutes, we're done. What is the orbital velocity of Mars? It gives us the mass of Mars, gives us the mass of the sun, gives us the radius of that orbital movement, whatever, track, whatever. The distance between the sun and Mars, we have it. So the mass of Mars, 6.4 times 10 to the 23, mass of the sun, 2 times 10 to the 30th, radius, 2.28 times 10 to the 11. I mean, we can set this up and go the long way, but I'd really love to say it's gravity that's causing this to happen. They're not touching. Force of gravity doesn't require touch. It's a field force. Fg is g times mass of the sun times mass of Mars divided by the radius square. Centripetal force is the mass of the orbiting body, being Mars, times the acceleration, centripetal acceleration. Mass of Mars cancels out. It's on both sides. It's always the smaller mass that's going to cancel out. So g, gravitational constant, times the mass of the sun, divided by radius square is equal to, let's change acceleration to v squared over r, so that we've got it in terms of v. The r on the right cancels the square on the left, so we've got gravitational constant times mass of the sun divided by r is equal to v squared. I'm not worried about getting the square root in there and making things messier. Let's just solve for v squared and then square root at the end. If that's fair, let's do it that way. To me, it's less cumbersome and less anxiety-driven, problems causing whatever. So G is 6.67 times 10 to the minus 11 times the mass of the sun, 2 times 10 to the 30th, divided by the radius, 2.28 times 10 to the 11th. We don't have to square the bottom for radius because remember, one of the radius canceled out in a previous step. So we're going to put this into our calculator, G times the mass of the sun divided by the radius, and that gets us velocity squared. We get that number, we square root it, we've got our velocity. It's kind of cool that the mass of Mars didn't matter. That just means if we get any radius from the sun, we can figure out the velocity because it factored out. We're getting 24,188.587 meters per second for the velocity. Last question, 2 minutes to go. How large must the coefficient of friction be between the tires of a car and the road if the curve, a radius of... Okay, well, we know we're talking about friction because it said coefficient of friction. Also, we know we're talking about friction because it's a car going around a curve. We're looking for the coefficient. Friction is our centripetal force. Radius is 85 meters. Velocity, 95 kilometers per hour. Man, the question maker just doesn't like us. They must love dimensional analysis. Well, 1,000 meters is 1 kilometer. And then 1 hour has 3,600 seconds. So we're going to take our 95, multiply by 1,000, and then divide by 3,600. We put it in this particular order so we can cancel out units. When I did it, I got 26.389 seconds. I'm sorry, 26.389 meters per second, because I'm left with meters and I'm left with seconds. Kilometers cancel out, hours cancel out. Force of friction is the centripetal force. Force of friction we saw earlier is coefficient times mg because mg is balanced with force normal. And centripetal force is mass times acceleration, but acceleration is v squared over r. Skipping a little bit of steps because we did them earlier. Masses cancel out, so coefficient of friction times g, or times 10, is equal to, take the velocity they gave us, 26.389 squared divided by the radius of 85. So I'm going to take my 26.389, I'm going to square it, then I'm going to divide by 85, get that solution, and then divide both sides by 10, so then I've got the coefficient of friction equal to that value. Let me get it through my calculator and just take a look. Looks like it's going to be like 0.819. That's it.